Hello, welcome to my YouTube channel today. Today's video is a continuation of my last couple of videos where I'm talking about building an external bus controller for an 8088 processor. This is V20, or the 8086 or V30. So today I've developed it a little bit further. I'm going to probably repeat a little bit from my two videos ago, just so that those who haven't seen that can kind of be up to speed. So the way this is wired up, I've got, starting over here, I've got 8284 clock. It's got a 15 megahertz crystal. This divides it by thirds, so that puts out a 5 megahertz click for the processor. It's connected up just pretty much the way the manual says to do it with the crystal. You've got your ready signals here. They really are meaningless in this because I don't use the ready off of this. But I do use the reset. So I've got some reset logic. I've got a capacitor and a resistor connected to the reset in, and a button which pulls this capacitor low, which resets and connects to the processor. The processor is connected up. The grounds on the pin 1 and pin 20 are connected. The 5 volts connected, and then the interrupt pins are connected, both low, the non-maskable, and the regular interrupt request. And then the click is connected to the 8284. Down in the bottom corner, you've got your reset, which connects to the 8284, and then a ready. Now the ready is tied into the homemade bus controller, and I'll go into that separately. The test pin is tied low, and then I've got a few of the control signals connected, because on this particular one, and in my last video I talked about doing this in maximum mode, I'm doing this in minimum mode. Minimum mode, really, it's about conserving space on the board and reducing the number of chips. If I was to do this in maximum mode with this current design, I would use an 8288 bus controller to generate the address latch click. And where I've gone with this, and this is for my notes, is I'm using the ALE pulse from the minimum mode from the processor to indicate the beginning of a bus cycle, which is probably about the most correct way to do it. And that's why if I was to do maximum mode, I would use an 8288, and that would almost be entirely just for the ALE. In my previous video, I showed how to generate the ALE pulse, which could be used instead, but if you want to reduce it down to one chip. The only problem with the 8288 is they're a little expensive and hard to find. So manually creating it may be the way to go if you can't source the chip. Sorry, that's a bit of a tangent. The hold request is tied low. Minimum max pin is tied high. Power's up there. So coming off the processor, well, let me talk about over here. We'll talk about the bus kind of towards the end. Off your address and data pins, address data 0 through 7, I've come over here to an address latch and a transceiver. And from the address latch, I'm going to the LEDs to demonstrate which address we're going to. And the transceiver now connects to a switch block, so I can tell it which opcode I want to put in. So from here, all I would do is wire in RAM. That'll be my next video, is the RAM, demonstrating the RAM working. This is just to demonstrate the bus controller itself. So for the bus controller, coming off of the processor in minimum mode, I'm using the IO mem output, the direction output for the transceiver, and the interrupt acknowledge pin. So those 3 pins. You could do it with 2 if you're not using an interrupt controller, but you definitely want to have an interrupt controller. So the IO mem, it'll stay active through the entire bus cycle until the ready pin goes high, and the direction stays active till the ready pin goes high, same with the interrupt acknowledge. And so by decoding those three, we can generate our own custom bus signals. On this particular one, though, I am using the data enable and the direction on the transceiver, and that's just to conserve pins off of the separate bus controller. Now, when I put the RAM on here, or the ROM, I'll go ahead and connect those up to the bus controller, the external bus controller, just to demonstrate they work. So for the bus controller, we have a ROM, and this is a W27C512, so it's 64K ROM. Going into this ROM, I have got address 0 through 7 connected to a counter. And I've got two counters here because each counter outputs 4. Let's just go to the high side. So this is the address 4 through 7. And this counter is connected, the reset is connected to the same reset as the first counter. 5 volt in. The rollover is not connected. Excuse me. The outputs are connected 4 through 7. The I can't remember what they're called now. The hold signals, though, or the kind of like a wait signal, is tied high on both sides, and the load is tied high. On the first one, though, the reset is connected. I'll go into that separately. The click is input from the crystal, and this particular crystal oscillator is 16 megahertz. And 5 volts, the rollover is connected to the second one. And then down here, I've got each of these holds are tied separately. This side I've got connected to the ROM, and this side I have connected to an external hold, which is the external ready input to simulate that. And then the load is tied high. So what happens is this will count up until the output, and this happens to be output D7 or output 7, drops low, and it'll just stop. So we can do something, and then drop D7 and stop. So we keep D7 high, until we've completed the bus cycle, and then we drop it. And at the same time, that goes here to an inverter, and when it drops, the ready signal goes high to the processor. So same pin stops the bus cycle and indicates that we're ready. To indicate the beginning of a bus cycle, I have the ALE coming off this in minimum mode, and it inverts it to the clear. So this will count up, drop low, and now this is just waiting. When you reset it, it's all going to be zeros, and it's going to start counting up through the ROM again, and until it hits that ready signal. And input into the ROM, I've got the IO mem coming in, I've got the DTR coming in, and the interrupt acknowledge coming in. I also have it displayed on these lights here, so we can see what we're doing. So from here, you've got 7 more outputs available that we can use for an IO mem read. Well, we could just do IO read, IO write, memory read, memory write, and you could do an interrupt acknowledge. And that leaves 2 more. Now, this happens to be an 8088, not an 8086. On an 8086, you've got your 16-bit bus, which is also 8-bit compatible when it goes to an ISA bus. And that is where you'll actually need a second chip to control, this is probably going to talk about this towards the end, but I'll talk about it now. So you have to have like a bridge. So you've got your data 0 through 7 and data 8 through 15 from your input, and then your output to the processor on the other side. But you also have to be able to go from the lower side, bridge across to the upper side of the processor. So on this, hold it upside down, I've got transceivers and latches. So 2 latches to latch the data and 2 for just transceivers to output and a bridge transceiver. And each one of these has control signals. There's about 6 or 8 control signals involved with this. And that would require a whole other chip, which would be synchronized with the counter, just to say, okay, we're going to read from 8, but we're going to read it up to 16, because we're going to go 8 to 16 bit and read from there. So that's the main purpose of this bus controller, is actually to go from 8-bit to 16-bit on an 8086, not so much for an 8088. It's just the 8088's easier to prototype with, but the concept is entirely the same. So I've got it wired up. As I said, the transceiver, which would be connected to some outputs here, is currently just connected to the regular outputs because it's fine for this particular setup. And it goes over to this switch block. So we'll fire it up and we'll kind of talk through some operations here. Over here, though, this is not really a part of the project, but this is, as you've seen in my previous videos, I slowed the click down so that we can actually see things work. So I just have 4 counters here that's got the click going in and a click going out of the last one to slow down the entire click process. It also demonstrates that the processor is running at its own speed compared to the bus, which is important, that they're not synchronized. All right, let's turn it on. Okay, so right now, as you can see on the LEDs, this top one's the ready, which you'll never see lit because by the time it lights up, it's already requesting a new bus cycle and dropping not ready. And then the IO mem, so on an 8088, memory's low, so if it's a memory read, it's going to be off. Direction is in, which is low, and then interrupt acknowledge is high because it's not an interrupt cycle. So this is doing a memory or code read from here, which we're set at no opcode. And on this, in the code here, about 8 spaces over, I tell it it's ready, in the which tells the processor it's ready. So it's counting up what I think is still pretty quick. I'll show it at full speed here. I'm going to just hold the reset, and we'll just put this at 16 megahertz. And there you go. It is just too fast. Actually, that actually doesn't even look like it's working. It's probably too fast overall. Let me just double check a few things. All right. Well, you get the idea. So I'll have to play with it a little bit. It should have just all been lit up. It was lit up earlier when I was playing with it, so something might be connected wrong. Let me demonstrate. So let's do an in. So obviously when it fetches code, it's going to fetch code originally, but let's go like an IO in. So in AL is E4. And you say, well, what port? Well, it's going to be port E4. So turn that on. I don't know if you caught that, but it counts up because it's loading the code, you know, the E4. So in, and then which port? E4. And now it's sitting here waiting for a ready signal from the bus controller, which it does not provide because it's not programmed to provide it yet. But you can see the memory I/O is now high, but it's still doing a read in, and it's not an interrupt cycle. and that's decoded on the ROM as well. Let's look at an out real quick. So I'm just looking at an opcode table here. Got out, let's see, out, AL, let's see, let's go to 6. So let's just turn this to E6. And this should, all right. So now it's saying out, so IO is high, out is high. It's not an interrupt on port 6, and you can see it counts up and stops there. So this here is demonstrating that because there is no code to tell it it's ready, it's just waiting forever. And that needs to be programmed in there. And that's where you would run, as you step through the ROM, you would have a, so this is an out, you would have a memory write signal out, but you'd also have your DTR signals coming off of here to set up the transceiver correctly for an out. And when it's ready, you would say ready, and then it would complete the bus cycle on the processor and go to the next step. Same thing with the, let's go back to 9.0, nope. The signals need to be programmed into the ROM to set the transceiver up correctly, so off of like say D0 and D1, and then you would have your memory read would come off of one of the pins and indicate a read cycle. So that's what I'll show in the next video. Is I'll put a ROM here. Probably leave the LEDs, but I'll put a ROM right here. Take this off and demonstrate it actually going through some code. And I'll put a little like out port so we can program it to do some read writes or at least an out and demonstrate it's working. And then I'll figure out maybe the 16 megahertz is too fast or something that's going on here, and that way we can run it at speed. Let me just try one more time before I end the video here. Yeah, that's still... There you go. That's it running at full speed and in a note opcode. It's just too fast to even count. And these are the lower address lines. If we had all 20 program or connected on here, you'd probably see some of the upper ones actually counting up. But it's going fast enough. You can see the ready light is lit, and you can see that these two here are staying low because it's only reading in. So anyway, thanks for checking out my video today. If you made it this far. Feel free to subscribe and check out for future content.